Hello everyone and welcome back to the fifth and final session of War Data Science Society's course into the Tidyverse. The goal of this session is to wrap up all the content we've been teaching for the last 5 weeks now, trying to kind of get you ready to go and work on your own data science projects by just kind of filling in all the gaps we haven't got to yet. So we're going to start with a quick recap of what we looked at last time. That last session was all about tidy data. And so we learnt a kind of formal definition for tidy data centered around these three rules here. So data is tidy if and only if each variable, that's a thing we can measure, is in its own column. Each observation, which is something we can measure things about, that must have its own row. And every value must be stored in its own cell. So we can't split a value across cells or have one cell containing more than one value. And these rules are interrelated. It's impossible to only fail one of them. If you fail one of them, you'll also inadvertently fail the second. And because of that interrelation, we can simplify these rules down into just a two-step procedure. To first put each dataset in its own table, its own tibble, and then put every variable in its own column. If you follow those two, then we'll naturally end up with tidy data. And the first set of rules is best for showing why data is not tidy and how to fix that. And then the second set of rules is better for actually trying to make tidy data from the start. We also saw some methods for dealing with untidy data, how we can go about fixing that. 4 key methods for fixing 4 common issues with data. Those were gather. This took a series of non-variable columns. Say if we had columns, one for each year, and then we'd gather those together into a key value pair, so just 2 columns, one containing the old column names and one containing the old actual data. And spread did the opposite of that. It took 2 non-variable columns where one of those columns contained variable names and spread those out into their own columns. And these were collectively known as pivoting operations, and there was a newer API, pivot longer and pivot wider, that you can use instead of these. And so the reason we had these 2 operations is that typically data is easier for a human to look at when it's in a wider format. And that's because we have, a landscape aspect ratio to our vision. And also it's easier for comparing things across because they line up nicer. But actually any data processing or any data visualization, really anything involving the Tidyverse, having a tall format or specifically a tidy format is much preferred. And so we can also use 2 functions for dealing with values split across cells or 2 values in the same cell, and those are separate and unite. We saw how to use those last time. Go have a look back at that if you want to remind yourself of that. It's also worth mentioning that tidy data, we started to hint at the end of the session, is a subjective notion. But depending on the problem you're trying to solve, the definition of tidy data might be different. For example, if you have a date, the whole date, day, month, and year, if that's what you care about, you're doing a time series analysis, then that is a variable. If you want to be comparing month by month performance, well then the month itself, the extracted month from that whole date, well that's the variable you care about. And so it's all very subjective. We saw diagrams and kind of the parameters for these functions in the last session. Go back and have a look at that if you want to. And so, why bother with tidy data? It all came down to putting in some work up front to make our lives easier in the long run. Because the Tidyverse, unsurprisingly, it's in the name, is designed for tidy data. And you can tell this because the way the Tidyverse does its operations, you can think about mutating a column. You mutate by taking an existing column and mapping a function to it. So you're almost taking existing variables and mapping them across new variables. And that sort of paradigm is known as a functional programming paradigm. And it only really works if you have variable-only columns. As soon as you start kind of splitting things up into non-variable columns, it all breaks down. And you need to use other approaches like a sort of iterative approach you would have in Python. And so to summarize all that, we put in that effort to get things in a tidy format. The Tidyverse is designed to work with that. And so it gives us a lot more power and it's a lot more expressive with the analysis we can do when we have that sort of format. So we also touched on relational data. Relational data is quite a big concept, we just touched on a small part of it, was mutating joins. We missed out on filtering joins and set operations. You can have a look in the book R for Data Science to learn more about that. And we saw three main types of joins, and these all differed on what they did when keys didn't match up between tables. If we had missing keys in a certain table, keys being the columns that we were joining on. So we had an inner join, the most simple type of join, only keep things that appear in both tables. Left or right join focused on one table and kept all the keys from that table. And a full join just kept everything, filling missing values with NAs. And so this was all governed by these keys, which is either a column or set of columns that appear in both data sets that we're going to join observations by. And when we want to join multiple tables together, we can do that pairwise. If we had, A, B, and C, we wanted to join all those together, well, then we would join A to B and call that, say, AB, then join AB to C. You can break it down into these pairwise relations. That's a very key idea in relational data. Okay, so we're now going to walk through some missing pieces, things we haven't covered, and then the main bulk of the session is all about more advanced visualization techniques. So, we're coming to the close of this course, but there's a few elements of the Tidyverse and R programming in general that we've kind of left out just to keep it simple or to kind of focus on the more exciting stuff. And so these techniques are going to be important for when you want to compete in the data visualization competition. So if you're watching this course by yourself, this is not relevant to you, but if you're taking part in one of our hybrid live courses, once this course ends, you'll have a few weeks to have a data visualization competition, hopefully with some prizes, but the details will be given to you in the live sessions. So, make sure you follow the team for kind of all the information about that. And so what we're going to look at is our scripts, how we can save a data frame, and how we can output a plot. So we're going to have a brief look at our scripts, and we did have a session, kind of a bonus session between first and second recording touching on this. We'll have a quick recap through it again. But this might be stuff that we've seen before, but it's good to have a recap anyway. So far, we've mainly been writing code directly into the RStudio console. That works fine for kind of experimenting with things. It's going to be very frustrating if we have long analyses or more complex things. You say we write in a load of commands and realize there was a mistake somewhere in the middle. Now we've got to rewrite all those, and that's an absolute pain to do. It's also very hard to share code. If I want to send my work across to someone else, I can send a screenshot of my console, I get the copy and paste output of that. It's not great. We want to send them a file that they can just click run and get the same output as us. It's all about reproducibility. So an alternative to this is using an R script. Also, these things called R notebooks. Those are a slightly more powerful tool. So an R script is for, actually I'll compare the two at the end, but if you want to learn more about R notebooks, then have a look at the bonus session between session 1 and session 2. So we can create an R script by going to File, New File, and R script. And we'll create something like this. And this is just a place that we can write our code. If we write some code in here, we'll start by loading up the Tidyverse. And we do, say, the head of MPG, press enter. That's going to run the code straight away. Whereas if you do it here, that's not going to run it straight away. I can press enter, nothing happens. It's a text file, and we can send things across to the console, putting our cursor on a certain line, run, or using Control Enter. That is a shortcut for that. And so, yes, we can write things in there, Control Enter to run a certain line, or Control Shift S to run the whole thing. I believe we can also use Control Shift Enter to run the whole thing. The difference being, I'm not really sure what the difference is. But I think there is a difference. You can have a look at that for yourself. Okay, and it's always good practice to start your code by importing the package you're going to use. So say library tidyverse at the start. And this lets people know what packages you're using and will give them an error right at the start that they don't have those installed. It is very bad practice to install packages for someone else. So do not put installations inside of a script. People should be allowed to manage their environments the way they want. Simply put in a library that will give them an error and tell them to install it for themselves if there's an issue. Another thing you don't want to do, something we haven't seen yet, but let's just kind of introduce it now. We have x is 1, y is 2, z is 3, so we're creating 3 variables here. We can delete a variable by using the rm command. This is short for remove, and we just put in the name of a variable. Here we do rm of x, going to remove x, kind of freeing up sorts of memory for our computer. So we often don't need to bother doing this. Modern computers have a lot of memory and are quite efficient in the way they store it and retrieve it. But if you have a very big data set and say you make a modification and copy it and don't need the old one, you might want to delete the old one. And one thing we can do to delete everything, kind of start afresh, this is often good for checking that our code runs from a clean start, is remove list equals ls. So first, ls lists out all of our variables, and then we can do remove list equals ls to remove everything. Now, you can do this in your console. You should never put this command in a script because you will delete everyone's environment, all the variables in someone's environment. They may have stuff stored there from before they ran your script. So do not do this. It is a massive dick move. Okay, so that's our scripts. We're now going to have a look at saving data frames and saving plots. So if you're working with very large data sets, running really complicated operations, these operations might take a long time to run. So we don't want to have to rerun them every single time. We want to save the output and then import that for later. And so we can do this kind of this more efficient way of coding by saving a copy of our data set to a CSV. So we know how to load CSVs, so just it's the opposite way, saving them back to a CSV. We can do this, whereas we had read CSV or read underscore CSV for reading a CSV file, you can write one using write underscore CSV. And so there's 2 main arguments. The first is the data frame we want to save, and that's convenient having it as the first one because that means we can pipe an output into write underscore CSV. And the second one is the path where we want to save the file. That's going to be a relative path relative to our current working directory. So look back at session 2 on reading files for a recap of what the working directory means. And so a note on this, by default, if we write a CSV file to a place that already exists, so we overwrite a file, it's going to delete the old one and completely replace it with the new one. If we want instead to append to a file, simply add on to the end of it, then we can add append equals true when we call write underscore CSV. We have an example of this? No. So let's do an example over here. Let's take, say, we'll do this in the console. Malpagal dataset, filtered down so that the class is 4-wheel drives. I forgot double equals there. Common mistake. So that wasn't one of the types. Let's go compact instead. Thought there was something like that. Perhaps that's in the drive type. There we go. So this is all the compact cars, down from 234, because there's 10 at the start there, down to 47 in total. So now we can pipe this, or we could save it to a variable and then save that variable. And we're going to pipe it straight into write underscore CSV. We don't need to put anything for the first argument. That's going to get piped in from before. And now we just have to specify a path. My current working directory, get WD to see where we are, is this into the Tidyverse folder. So let's create a folder here called output. I'm going to save it into output / compact cars.csv. I can now run this, go into output here, have this this file with only the compact cars. And now we could load this back in using read underscore CSV. If, say, we wanted to now add the subcompact cars, we could use append with 2 P's. Oh, jeez. There we go. To append that to the end of this file. So if we run that, now look at it, those will now be put on at the end. If we hadn't used append, look at that now. The whole thing's going to be deleted and we just have the subcompacts. Okay. Now we'll look at outputting a plot, so saving a plot. And we can do a similar thing to writing a CSV, but for ggplot, and that's using the ggsave function. And so This time we don't have to specify the object that we're trying to save. By default, it's going to use the last plot that we displayed or created. We do still have to specify file name we want to output to, but here's where it gets a bit weird. Whereas with write underscore CSV, we specified the whole file path, so the location of the file and the file name. With ggsave, we split that into 2 bits. The first argument is the file name itself, and then we specify the path separately using an optional path parameter. So for example, if we had wanted to have a file name called my_plot.png and save it in its output folder, we'd have a file name of my_plot.png and a path of output, whereas before we just had the whole thing together. And so there's quite a few in fact, additional parameters that you can specify. You can look at the help file for ggsave, so !ggsave to learn more about that. We can see different scale, dots per inch, the units we're using. We can use that to specify exactly how we want the plot to be outputted. And ggplot is clever when it comes to saving, in that it will guess the correct file type by what extension you use. So save to a .png, save to .png, .svg or PDF, it will do those automatically. And for more obscure file types, you might have to specify the device manually. Let's just give an example of that. Let's take a very, very simple plot of mile per gallon. So mile per gallon, kind of X is highway, and Y is city mileage. So do a GM point. So we can run that and then use a ggsave after this. And so it's going to use the last one. We don't have to specify the plot we're doing. I want to save it as, let's call this mileage dot, let's do SVG. I'll say support, support isn't the right word, scalable vector graphic, which is it's an image that you can scale to any size and it won't lose resolution or become pixelated. Very popular format for saving graphs because you can scale them on a presentation without them getting all fuzzy. And that's going to save that in our working directory. We want to save it in the output folder. Is that path equal to output? Let's run this here. And okay, so the problem here is that I didn't have SVG Lite installed. Let's install that quickly. This is like an optional dependency of Tidyverse for when we're outputting SVG. We just did install.packages and SVG Lite. Might be similar things for PDFs and other file types too. Okay, now that is installed, we can run this code here, and you'll see it saves a file. These are in inches. It's saved to that path we specified. So we go in here into Tidyverse output. We have an SVG file here. RStudio can't open that directly, but let's open this. We see there it is, an image, and it's an SVG, so it scales nice. I can zoom in. We don't lose any resolution there. So there's a few parameters we might want to change. I'll give an example of one here, which is the scale. Let's do this for 3. That's going to make everything 3 times bigger. Run this again. Let's have close that. Look again at the output. And so the output now. Okay, that went the other way. So now that the plot is 3 times bigger, but the points are still the same size, everything looks a lot smaller. So you can mess around with those sorts of things to get different types of plots. Okay, so that's all we have for kind of notes on tying things together. We're now going to spend the rest of the session looking at advanced data visualization. Okay, so where are we? We're back at visualization, full circle, in fact, right back where we started. It's been a long time coming. We've seen some basic visualization using scatter plots and line plots. But I mentioned right at the start, there's loads of geometries. We've not taken advantage of barely any of those. The reason why we haven't is that we're still lacking knowledge of 2 important things, 3 really, which are statistics, positioning, and coordinate systems. We're going to introduce those through some examples, and then we'll, that will open us up to using all sorts of geometries and creating some really interesting plots. Okay, so when I say advanced, what do I mean? There's still, here's the thing: ggplot and all the Tidyverse is a very massive world. There's a lot of stuff you can do with it, and there's really a lot of powerful stuff. So even in this session, we're only going to kind of scratch the surface of what ggplot can do, or the full scope of customization. So we're going to cover the most important areas and the most important things for making some exciting and good-looking plots. So for so the three things I mentioned before, we have these things called statistical transformations or stats, positioning, coordinate systems, and finally theming, which is how we make our plot look a certain way. And with this, there are things we're not going to look at. A whole kind of aspect of ggplot is the notion of scales. We're not going to look at that at all. You can look in R for Data Science to learn more about that, or on the ggplot cheat sheet. Search that on the web. So it's a lot for one session, so stick with it. But this is the final hurdle. So once we have this sorted, this will cover almost everything you want to do with ggplot. Okay, so we're going to start with the most complicated idea, and it gets a bit easier from here. That is statistical transformations. Okay, so we're going to start with a motivating example. So we've seen scatter plots and line plots before. We can also use ggplot to create a bar chart. We do that using geom_bar. And so we can create a very simple bar chart. So we're going to have ggplot. Our data is the diamonds data set. Let's have a quick look at that to remind us. Diamonds look something like this. So it's got different diamonds, like quite a big number of them, in fact, and information about their kind of quality and cut and their sizes. And so we're going to use this data set. Actually, we don't need to specify this data equals mapping spelled incorrectly here. These are optional parameters. I think we recall that from a previous session. And so we can just do ggplot and diamonds. Actually, let's have a look at this plot here. I'm going to remove those unnecessary sort of naming there. So we run this, we get a plot like this. So our x-axis is the cut. So the different cuts of the diamonds, kind of from fair up to ideal, and then how many of each of those we have a bar for that. Okay, so looking at that plot, you might notice something a bit strange. So cut on the x-axis, we recognize that. We set the x-axis to be the value of cut, so no surprises there. But what about the y-axis? We have this variable count. Like, where did that come from? We didn't specify any variable count here. Count wasn't contained in our data set. There's no column here called count. So where did that come from? It's it's not part of our original data set. And so this is known as a statistic. Very simple graphs like scatter plots or line plots will plot the raw values of our data directly. But anything more complicated, such as a bar chart, will calculate these values or will calculate new values on the fly and use those. And these new values are called statistics. And so bar charts, histograms, or frequency polygons. So I won't get into what these things are. If you're not familiar with them, just have a search for them. You can find an image. How these work is by binning your data into groups and then counting how many appear in each bin. In this example, we grouped it into the bins, one for each level of the cut, and counted how many was in each bin. We do a similar thing with geom_histogram, or say, we'll want a numeric thing here. Say let's go for price. You see here we group them into these different bins and count how many are of each of them. I think log price actually gives a better image here. There we go. That's a bit nicer. Okay, smoothers. So actually we saw this when we did geom smooth, but maybe didn't recognize what was going on there. That what geom smooth does is it fits a model to our data. It could be a linear model, could be a more complicated additive model, and it plots the predictions of that model. When we had our data and then a smooth line going through it, that smooth line wasn't in our data set. That was created or kind of transformed from our original data using a stat. And a more complicated example, box plots. Let's do box plot here. Let's do a geom box plot where the x is going to be the cut and the y is going to be the logarithm of the price. Here we get something like this. So the cut we recognize, the log of the price we recognize too. The actual data we're plotting here, so the maximum, the minimum, the median, and the quartiles, well, that's not data directly available in our data set that had to be computed. And so again, a stat happened here, even though the aesthetics are still the ones we set out originally. And so the algorithms that are used to calculate these new values are called stats. The thing I said earlier that the stat was the new value, that's a slight mistake there. The algorithm to create the new values are known as stats. And so we can find out what stats are used or are valid for a certain geometry by looking at the corresponding help page. For example, let's have a look at the help page for geom_bar. And we'll see here, if we look at stat, the stat being used is the counting stat. And so these also kind of, these go in both directions. Kind of there's nice mappings between stats and geometries. If we looked at the help page for for stat count, let's do this. It's kind of the opposite way around. Then actually, this is the same help page, but stat count, the default geometry is bar. You can see that every geometry has a default stat, and every stat has a default geometry. And so if we look in geom bar and scroll down a bit to computed variables, so there's a lot of information here, but computed variables is the bit we care about. We see the values that get computed by the corresponding stat. So a bit confusing here. It's the stat that computes the variables, not the geometry, but it's in that geometry's help page. So they're all very closely connected. It can get a bit confusing, but that's just the way it is. So two variables get computed, account, which is how many numbers are in each bin, and then prop, which is kind of the proportions, so between 0 and 1, of how many points are in each bin. And so these are computed by the stat, and we have access to these if we want to. And so that's where the count came from. It's one of these computed variables for the data we give. And so every geometry has a default stat, so in reality, we rarely have to worry about what the default stat is. It's normally a sensible one, and things work just fine. And these new variables might be computed. We don't worry about it. It's what we were after in the first place. And so this might seem quite esoteric, because in reality, in 99% of plots, we don't care about this sort of stuff. But it's worth knowing for when you want to do those edge cases. And we'll give an example in a moment of an edge case, and it's worth knowing this because otherwise there is no way of doing it using ggplot. So let's have a look at an example when we can overwrite a stat to not use the default. Sometimes we don't want to use the default. For example, we might want to use a bar chart, stat underscore identity. So that count is the default. That counts how many things are in each bin. But what if we had data where we actually had the numbers or the counts already? What would we do in that case? So let's take this this data set here. Something like this. It's created using a tribble, which stands for transpose tibble. It lets us write out a tibble in a column-wise way. So to look at that, see what that contains, it's something like this. And notice here, whereas with say the diamonds data set, we didn't have a count. We just had this variable cut, and there was repeats of this. And multiple very goods. We wanted to count how many there were of that. Whereas with salaries, there's no repeats. We simply have the value computed already. We want to plot that value directly. So let's have a go at plotting this using geom_bar in its default state. So we won't change the stat. We're just going to plot it as it is. And we're going to do that without using the y static. Because as we saw before, if you go back a bit, geom_bar just takes an x static. Again, I'm going to get rid of these unnecessary arguments here. To run this, and we get the following plot. Each person's name and a count of 1. Because by default, geom_bar is using the stat count, so it's counting how many observations or how many occurrences of each name come up? And the answer is 1. We get a completely meaningless plot, which says that, I guess, every name in our data set is unique. What we want to do instead is to set the stat equal to count, or is it stat underscore count? Oh, no, sorry, it was count already. I want to set it to identity. Identity just means keep things as they are. If you're familiar with maths, there's the identity function, which means map everything to itself. So don't change anything at all. But in doing this, this stat's going to require different inputs. We're going to specify what our y is directly, because that count tells us to use the count for y, but for identity, we have to say what we're using it for. I think, I can't remember what it was. Oh, it was salary. So we plot this, and now we get the graph that we were after, where we have the salary as each of the values here. Actually, this is unnecessary. We could have just used geom_col instead. We saw this in the end of last session. A geom_col is very similar to geom_var. In fact, it's exactly the same, but the default stat is identity. So there's many cases where you have multiple geometries which are almost exactly the same, just with a different default stat. So there we go. geom_col does the same. Okay, so yeah, as mentioned, we could have done this with geom_col as well. Okay, so another example of overwriting mappings. This is a different idea. So we can overwrite default mappings using the transform variables that are computed. So if we do a default bar chart, then well, actually, let's break this down bit by bit. We'll ignore the slide. Let's start with the default bar chart that we had here. So we have, let's get rid of this stuff. It's very redundant. Here we go. So this is the bar chart we had before, something like this. Let's say instead that rather than having the counts here, we wanted to know what proportion of the total diamonds each category made up. So this might be something like, I don't know, 2, 3, 4%. Well, we can do that by using one of the computed variables. If we go down to computed variables, we have count, that's one we're using by default, and prop. So we can overwrite our y. Actually, let's start with, so when we write this, what we've implicitly written, this is what stat underscore count does in the background, is y is equal to ... count ... And this ... notation is used for representing computed values. So this isn't a real value, the ... signifies that it's computed. So if we run this, this is exactly the same as what we had before. This is kind of done in the background. We can specify it manually. Instead, we could use prop instead. That's going to give us the proportions rather than the count. But there's a small problem here. And that is that these proportions are group-wise, but what are our groups? By default, the group, I think we might discuss this in one of the homework exercises. The group is kind of the intersection of all discrete variables we've used. And so here cut is a discrete variable, and so our groups are each of the cuts. And so what this is saying is that for each group, so for each kind of cut of diamonds, that individual cut makes up 100%. And like that's trivially true. 100% when there's only one thing is the whole thing. What we're going to also have to do is specify that our group is a -1. That's going to reset the grouping so that everything is in the same group. And so now these are all in the same group when we're doing the proportions, and so get these different percentages that we wanted here. Something like maybe 0.34% here, and different percentages here. Okay, now let's have a brief discussion of some more geometries. Because really, the main thing we were missing was a knowledge of statistics. Now that we have this, we're now free to use all these different types of geometries without worrying, you know, where did that column or where did that axis come from? And so here's a very brief summary of different geometries we might want to use. You can get an even more comprehensive understanding by searching for the ggplot2 cheat sheet, which just contains all of the geometries. So let's run through a few of them, and their use cases. Say we have one single variable. We might want to use a histogram, a bar plot, an area plot, a density. I mean, let's have a look at one of each of these. Actually, no, we won't do in this session, but in the live session, if we have time, we'll have a look through them. We'll just run through what you can do here, have a go using them yourself, look at the help pages. If you have two variables that are both continuous, we have geom, we've seen scatter before. Another one would be geom label, basically a scatter plot, but we have boxes full of text, or geom text, which is just the text without the box, or geom rug, which creates a rug plot, little lines at the bottom of the plot. If one is discrete, we have geom col, or geom box plot, or violin. Violin plots are very interesting plots. They're basically two density plots put back to back. If we have two discrete variables, then geom count is the best one to use. That's kind of a 2D version of a bar plot. If we have kind of bivariate data, so the idea being there that we have two different variables and want to know what distribution they have over those two dimensions. We have geom bin 2D, think about like a 2D histogram. Geom density 2D, basically a heat map, or geom hex, which is like a it's like bin 2D with hexagons are the best shape. And so you can find out about the aesthetics for these by looking at the help pages. And if you're in the hybrid live sessions, we'll work through a few examples of the best ones. Okay, so we're now going to talk about adjusting the positions of our aesthetics. So let's do some coloring. Let's take a bar plot and make it a bit prettier. So we saw with geom point and geom line, you can specify the color of the point or line using the col, color, or color, the American spelling, aesthetics of that geometry. Sorry, got my words there. And so if we try and do this with a bar chart, we're going to get a different result. That's because bar charts have two aesthetics for controlling color. If we use just color, that's going to control the outline color of the bar. So here, if we set geom bar with our color being cut, then we just get an outside which is controlled by this cut. What we wanted to do was to use fill. That's going to control the inside. By default, there is no outline; it's set to NA. Okay, so that's fine. What happens when we set the fill aesthetic to a different variable than our x? So in this example, with x being cut and the fill being cut, quite boring. What happens if we set x to be a different value to the color? Well, then we end up with a stacked bar chart. Very pretty, very minimal effort to get something very nice. We take Diamond's data set, geom bar, our x is the cut, fill is clarity. And now for each cut, we stack up the different clarities in a stack bar plot. So the same thing would also have happened if we had used color instead of fill. But this is not going to be as pretty. If I use color here and run this, get this very ugly plot. You can do it if you want to. Okay, that's good. But what if we didn't want a stacked bar chart? What if we wanted them side by side? Wanted them to fill the whole height and be proportional? Well, then we can control this by using the position parameter of geom underscore bar. By default, this is set to stack, which is why things get stacked up. And so there's three common other options for this: identity, dodge, and fill. So identity is used to place things literally where they would normally appear if there wasn't any positioning. So again, identity means mapping things to themselves, don't change anything. And so this would cause the bars to overlap, and so we wouldn't want to use it unless we had alpha set to a non-zero value, to a non-1 value, so some low value, that we had transparency, or if we had fill as NA and an outline color. So yeah, I think we have an example of that there. We'll come back to that in a moment. We could use dodge, and that's going to place things side by side. So let's actually give an example of that now. Let's take this original plot here. We have it here already, and add position equals dodge. And we do this outside of the aesthetic mapping because this is a separate parameter. And so here, let's go back to fill. It's something like this, where these are all put side by side. I guess also look at the last one. So the last one is fill. Works similar to stack, but it makes sure that all the bars have the same height. Now we're looking at the breakdown within each group rather than the absolute values. We have fill here. You get these comparative plots here. Very useful for comparing the breakdown of each one. Because these now all go up to 1, you lose the absolute counts. I can't tell whether ideal or fair has more diamonds in total. You can experiment with these by kind of messing around with the previous code. One example, using position equals identity, is something like this. It's really ugly. We set fill to NA to get rid of the fill, and the color to be the clarity. And the position identity means plot things where they would have originally been. And so we now have these overlapping boxes here. So like I1 is a small box here, then we have some large boxes over the top. You would rarely want to do this, but just in case, the option is there. Okay, we're also going to talk about jittering here. So scatter plots have their own position parameter. In fact, all geometries have a position parameter. And this defaults to identity. And so another option is jitter. Whereas identity plots things exactly where they were, jitter adds a bit of noise. And this is really important to reduce overplotting. That occurs when you have loads of data points in the same place. So let's give an example of this with the mile per gallon data set. So the most common reason why we have overplotting is if we're plotting data that's been rounded. If I have a look at highway and city mileage with a geom point, get something like this. Actually, this isn't a very fair plot. If I use geom count instead, in which the size of the points is determined by how many points share that same position, you get a different picture. Actually, what appeared to be a single point was actually loads of points stacked on top of each other. We couldn't see that. So one way around this is using geom count. Another way is to use geom underscore point with position equals to jitter. Adds a little bit of random noise that we kind of counteract the rounding of our data to the nearest integer. And now we can much better see that whole pattern without kind of obscuring things by overplotting. And another option is using geom underscore jitter, which is exactly the same as geom underscore point, but with the position set to jitter by default. Another option would have been setting transparency. We add a bit of transparency. You see by the darkness of the points how many were there. Okay, so the final thing we're going to look at is coordinate systems. And coordinate systems are used to control our x and y coordinates and how those kind of map to one another. And so one thing we might want to do is flip our x and y axes around. And so this is very useful, say, if we want to have a bar plot that goes horizontally. Because I believe, okay, this is where I might be old-fashioned. It used to be the case that if you did a bar plot, that you couldn't set only the y aesthetics. So if I do, let's start with this. So we can do a bar plot of class. There we go. Now I'm going to try and have the y set to this. And this used to not work. Okay, it does work now. It used to be the case that this didn't work at all. And you had to use a coordinate flip to change this over to the other way around. Still, it might be the case that you've set everything up to work with x and y the way you like it. The last step you want to do is flip things around. So to do that, you can add one more layer, which is a coordinate underscore flip layer. That's going to swap those two around. So here's an example with a box plot. Again, you could have just swapped out x and y here, but you could also use coordinate flip. And I believe there are still some cases in which coordinate flip has to be used. We'll see in a second there's a more important coordinate transformation you can't get around using other methods. And so typically we'd want to do this, say, if we have very long names for our x-axis, we want to put them on the y-axis to have them spread out across. Or it just might work better with the shape of the data we're plotting. Another thing we might want to do is to fix the aspect ratio. By default, ggplot will scale our graph to fit the available window. Let's do a plot Here's an example of a hex plot like this. And I'm going to make my plotting window really, really narrow. Okay, make it a bit taller. So we've introduced a problem here because both city and highway mileage are measured using the same units, which is miles per gallon. And so really we want a like-for-like comparison here. If I go across a certain length on the x-axis, this is a length of 10, then go up the same amount on the y-axis, well, that's an increase of 20. And so a straight diagonal line here, kind of a 45-degree angle line, doesn't correspond to a one-to-one relation. And that's a problem that makes a confusing graph. And in fact, you might want to use this to mislead somebody. You should also be aware that that might be used to mislead somebody. And we can get around this by using quad underscore fixed. That's going to fix the aspect ratio, so no matter how big I make this, always has an aspect ratio of 1. And note it's not the aspect ratio of the whole plot, but just the actual the panel where we're plotting things. Now an increase of 10 in this direction is the same length as an increase in 10 in this direction. And we can change this ratio using ratio equals, say, 2. That's going to mean an increase of a certain length in the x direction is now twice the increase. Sorry, is that the right way around? So if we increase 10 here, we increase by 5 here. So double the increase in direction. We can change that to be whatever we want to have there. You might want to use this, say, if you're plotting centimeters against millimeters, you want to make a ratio of 10. Okay, so the last coordinate system we're going to look at is polar coordinates. And this is a really powerful thing to do. And what this does is it treats our x and y coordinates as r and theta respectively in a polar coordinate system. I think that might be the wrong way around, in fact. I think it might be theta and r, but you can manually specify which you want to be theta. So I think we're going to manually specify them here just for clarity. Actually, I mean, let's see here. So sepal width is the one going outwards. And that was our y. So here y has been mapped to r. So yeah, I think I had these the wrong way around. Okay. The idea is we have our x and y. We use quad polar, and that kind of converts us to a polar coordinate system. So here we have an iris plot. So sepal length and sepal width. The x became the angle. So this angle around here, 5, 6, and 7. And the y is now the radius going out here. So this might seem very pointless. You know, this is a very confusing graph. Why would we want to represent our data like this? And the answer is, well, this is how we do pie charts or coxcomb or radar plots. If you've not seen coxcomb or radar plots before, I think we have examples of those in the homework, or you can have a search for them. And you might be asking, well, why can't I use geom underscore pi? Why doesn't that exist? And the answer is, if that did exist, it wouldn't encourage you to learn about these coordinate systems. And the beauty of these coordinate systems is that they're much more flexible and expressive than just having pre-canned methods with, say, a pie chart or a coxcomb plot. If you understand the notion of a coordinate system and polar coordinates, you can create your own plot types that don't already exist using kind of polar bases. For example, I did some work a long time ago in which I created a new type of plot for a company I was working at that they couldn't create using Excel. It wasn't available in ggplot, but because I understood polar coordinate systems, I could make it from scratch, and it, was very expressive and very important, useful for the type of data they were representing. That's the reason why we'll learn the nitty-gritty, just so you have the flexibility. We want to do some more advanced things. So this is how we would do a pie chart. It's a very ugly-looking pie chart. We'll learn when we get to theming how we can tidy it up a bit. So, a bit confusing how we make this. Let's break it down bit by bit. Let's start with just this first line here. So actually, we'll need the first 2 lines to see it. So, what we're going to do is create a bar chart, because all a pie chart is a bar chart in polar coordinates, and specifically a filled bar chart, so one where we're filling the whole height. You can think of this kind of rotational axis here as being our y-axis going from 0 to 1, and can we fill out between there. What we're going to do, we're going to map our aesthetics. The fill is going to be our class, and x is a dummy variable, -1. And what this is going to do, just going to create everything in the same plane of x-axes. I'll give an example at the end of what will happen if we have multiple of these. But for now, mapping this to -1 just to say put everything in the same column. And then we fill with class that's going to create a stacked one by default. We set the position to be fill. Now what we're going to do, we're going to add in all the coordinates, and we manually specify our theta. Theta is y. So it's probably good to manually specify whether you want x or y to be theta to avoid any complication. That gives us this. So we'd have done our theta as being x, get this plot here. Which, I mean, yeah, that's a plot that doesn't exist. Is it informative? Probably not. But hell, if you wanted to make a dartboard, or perhaps like use some sort of bullseye, that's how you would do it. That's the beauty of using these coordinate systems, is that you have complete flexibility. Anyway, back to this. So now we have this this -1 as the label for our. Sorry, that's not the issue. We have this issue of count here. This we'll learn how to get rid of using theming. We have this count at the bottom. That's the name of our y-axis, and we want to of our x-axis. Okay, sure. I'm confusing myself here, and we want to get rid of that. And do that by using x equals then some empty quotes here. That's going to. I mean y. There we go. Yeah, y. Because yeah, our y was that count going up, whereas our x-axis is just blank. So here we set y to be empty. Just get rid of that label here, and all the other formatting we'll learn how to remove that when we get to the theming. Let's just give an example of what happens if we put a variable here. That one, let's do drive type. Then we get this here. Which, God, this is a peculiar plot. I guess it's kind of like, it's multiple pie chart and then donut plots. So this could be quite useful. We can see here that for different drive types with different breakdowns. So for example, I guess, so 4-wheel drive is in the middle, and most of those are SUVs, whereas front-wheel drives, none of those are SUVs. So, I mean, hey, if you want to do that, the option's there, and let you do these really crazy types of plots. Okay, so the last thing we're going to look at is theming, how we can tidy up the plot, make things a bit prettier. So, we're going to start off by talking about complete themes, and so ggplot comes with several complete themes, and these control all non-data display. So data display is controlled by aesthetic mappings. For anything non-data, say color of this background here, which is grey, that's controlled by theming. And so the default theme is theme_grey. Ironically, this is one of the ugliest themes in several people's opinions. And we can look at a list of all themes by looking at the help file for any theme. So pick out theme grey, look at the help file for that, and we can see here a list of all of the different themes. So one example is theme minimal. Back to that in a second. And so some of my favorites are theme classic, black, white, and minimal. And we can change the theme of a plot by just adding an extra layer. We're used to ggplot by now. Do a plus, add a new layer. Take the last one here, and we'll do plus theme minimal. That gives us a plot here where the background is no longer grey and things are reduced down a bit. We can have theme classic as well. Then that's going to give us some black lines. There we go. So various different options there. Now, we probably don't want to add that to every single plot that we do, especially if we want the same theme for all of them. In which case, we can use set a default theme. So the default theme for a plot is taken from whatever the value of theme get is. So here, theme get contains all the data for theme_grey default. And what we can do, we can overwrite this by using theme_set and then putting a theme inside of that. Say theme classic. And if we were to run this, that would reset that default theme So everything from now on is going to use that default. Now, it's worth noting that when we use when we use theme underscore set, it returns the old theme as an output. And so it's good practice to assign this to a variable old theme, or to an object old theme. That way we can go back to things after if we need to, or if we're running a script on someone else's computer, we don't delete their custom theme if they had one. This way we could end our code by so let's run this, create a plot without using that theming. See, it's still theme classic. We could end our script by doing theme underscore set old theme. Set things back to default, run this again, no black line. Great. And so that's controlling kind of the complete theme. How can we control kind of more fine-tuned elements of the theme, so individual components? And we do that by adding a theme layer. This is a function that takes a literal ton of parameters. So if I do theme, look at this, we'll see all of the different parameters that this can take. It goes on and on and on. And there's even a dot 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 for even extra things. And so we can set any of these different parameters, each one controlling some element of our plot. We can set them to be the value of an element. 4 main types of elements. Element underscore blank, which basically just removes it. Element underscore rect for rectangles or kind of anything blocky. Element underscore line for lines, and element underscore text for text. And the one of these that we choose is going to depend on what aspect of our plot we're changing. If we're changing, say, the axis labels, we'd use element text. If we're changing the plot background, that kind of rectangle at the back, we'd use element underscore rect. For our axis lines, we'd use element underscore line. And then inside of these elements, we then specify exactly how we want to set the aesthetics or kind of the look of those theming elements. And so you can look at the help pages for these to learn a bit more about them. But let's have a look at a few examples here. So let's take this plot we had here. And for a start, let's get rid of this label here. So this is the x-axis. Okay, let's get rid of these ticks here. Those are the ticks on the y-axis. So what we're going to do is theme, and then it's going to be axis. And I'm just familiar with these. You can look at the help file if you don't know them. Axis.title.y. I'm going to set that to element underscore. I mean, remove it. Actually, let's get rid of the whole text. So I want to get rid of the ticks as well. Okay, sorry. See, I guess I don't know these as well as I thought I did. The text is the actual labels, and then the title. Sorry, yeah, the text is the text on the ticks, and then the title is the actual title itself. So we can just separate these by commas. We have ticks as well, so let's get rid of those ticks on the y-axis. There we go. That's removing stuff. Let's do panel.background, the element underscore rect. It's a rectangle. And the fill is going to be black. Why not? Ugly as hell, but there we go. And for a final thing, we can't see that too well. Let's go for light pink. I think that's a valid color. Go. And final example, let's do axis dot text on the x-axis. Instead, it's equal to element underscore text. And what we're going to use here, let's do face equals bold. There we go. We now have bold text there. So lots of customization. We can do a lot of things with that. Okay, so coming to the end now, let's summarize all that we've done. So the most exciting part of this course is the graphics. It's going to be the final part of any of our analyses. It's the thing we show to the world. So let's just kind of finalize a recap of everything in the grammar of graphics. Sorry, that's a lie. Everything we've covered in the grammar of graphics. There's still a lot more to learn, but for most cases, this will be fine. And so this foundational idea is that we can build up these layers and we have a really flexible API for creating these plots. As that allows us a very powerful, expressive way of creating literally whatever we can imagine up. So the following template is kind of a summary of everything we've seen. So start with ggplot, that's a base layer, pass in your data. Put aesthetics in here, global aesthetics, or you can put them in a geometry. use the mapping for that. We don't have to specify mapping equals. We can just put them in directly. Then also put mappings on the outside for manually set aesthetics. Sorry, they wouldn't be called mappings in that case. Manually set aesthetics outside. We can set a stat, which is going to be how our data is kind of algorithmically converted into variables, and a position, which controls how our points or how our geometries are positioned. We could then add multiple geometries if we wanted. That is on top of each other. Add a coordinate system, add faceting. We could add theming at the end. This is typically the format you go for. And there's some other things we come across, like the labs function for creating labels. And there's even more things like scaling, which we haven't had a look at, but you can in your own time. So going further, ggplot does not end there. And the beauty of ggplot and R being open source is that there's loads of extensions that you do even more powerful things. Here are a few of my favorites. We have gganimate. This is used for taking a static ggplot and turning it into an animation. It's really simple to do. We basically just add an aesthetic for what frame we're on, and we can create some amazing things doing that. So please do have a play around if you have the time. ggthemes gives us more themes, more geometries, and more scales, which we haven't looked at yet. ggrepel, love this. It's for creating text geometries that automatically move themselves to stop text from overlapping. Super smart, super easy, and create some beautiful plots. And finally, geofacet holds a special place in my heart because I've contributed to this. It is a way of faceting by real-life geometry, or real-life geography, sorry. For example, we could create a map of the UK in which every different region, so northwest, southwest, whatever, we had some sort of like plot for that, and those facets were arranged in the actual shape of the UK geography. In the hybrid live session, I'll give an example of this, one that I made, but it's worth having a look at if you search for that on the web. Okay, so with that, if you're watching the live course, if you're watching the pre-recorded course, that's the end. Thank you for making it this far. I really hope you've enjoyed watching and are keen to learn more about Tidyverse and apply it to your own sorts of problems. If you haven't already, make sure you check out WDSS on Facebook. More importantly, we have a main Facebook page and a community group, so WDSS Community on Facebook. And this is where we post opportunities to get involved with society, opportunities to contribute to our research blog, so our research team can help you in producing your own interdisciplinary work, and many more opportunities for careers, for education, for everything. So please join that group. Best way to kind of get involved with the society and take advantage of all the things we're offering. And so if you're watching the hybrid live session, we'll now take a moment to talk about the data visualization competition. But for now, thank you for watching. See you soon.